Hi, my name is Vahan Davoudian. I'm a physics experimentalist for 30 years. First of all, I'd like to thank so many people that emailed me. They love these theories, and I will continue to do the same thing. And I appreciate that. That's great encouragement for me. Thanks a lot. And I'm a physics experimentalist for 30 years. I have always replicated most, experiment done with, famous scientists as much as I could if I had the material and everything else. But now, today, our topic is going to be laser, which is the most important thing in our life. And it's just, it's so versatile, so indispensable. It is used in every concept in our life. So, I start this laser, and then I had so many speeches in universities like DeVry College, and then Regis University, and CU Boulder. They loved it, and then I made friends with so many physicists. And even though I don't have a PhD, but they love my ideas because most of my experiments are unique, and I have never seen in any books or any textbooks or any lectures, even in a college or university lectures. And now today you are going to love this because I added two more concepts which has never been discussed with scientists for the laser, and you would love this. And I'm going to start with this. And laser means its acronym is for light amplification by the stimulate of emission of radiation. And in fact this started with theoretical work of Charles H. Townes. And in fact, this was a theory, and then, there was another scientist, Charles H. Townes, and Arthur Schwallow. And, they didn't do exactly the way Mr. Theodore Mayman did. And in fact, this was invented in 1960s by Mr. Theodore Mayman, and that was breakthrough in science, and I don't know how it changed our life and everything else. So, and he was investigating for the lacing. Lacing means the medium, that tube, that laser tube, whatever, it can be semiconductor, it can be gas, it can be solid, but he used ruby rod, and I will explain why he used his name was Theodore Mayman. He was an American physicist, and he was so genius, and then he just finished the job, whatever Mr. Charles H. Townes started. And in fact, what they did, he just did everything in a fantastic, the precision was unbelievable how good he was. And then it was in 1960s, and in 1970s, they produced, the laser which would be continuous light instead of, pulses. Anyway, this is amazing. When you have like ordinary light, like, it doesn't matter, LED or incandescent or, discharge gas lamps or, fluorescent lamp, overall the photons or, all the lights are so many, they are, randomly everywhere. They just go in any direction, and it's called incoherent. Well, but when we have laser, it's coherent because there is just one color and everything is in the same phase, and then they have a lot of power. In other words, they can penetrate, they can go long distances. So anyway, it's called the monochromatic light, and it's so coherent. And I will explain exactly how it works. I have another one. Let me put this on. In fact, this is almost like 4 stages. Well, it doesn't matter what kind of lacing you use. It doesn't matter. But the overall, let me just post this up. You can see. I have to take this off because it might interfere with this. Yeah, I just take this off. The basics are like this. This is what Mr. Theodore Mayman used, and it's called flash tube. And you can see it's just a simple thing, but you know there's a lot of science involved. And you can see here there's a mirror over here which is 100%, or that is the best probably mirror, but this one is almost 95%. I will explain later why. So the first step is, you know, the tube, when the photons are going in, they are absorbed. So you can see the flash is, you know, it's going inside. And the second stage, you know, when the photons are absorbed, simultaneously they drop to the, you know, low level. So what happened at that time, spontaneously dropped to the low level. Well, when the electron, if you remember, this was a Niels Bohr idea in 1900, and then he got Nobel Prize for this. When they drop to the lower level, so they are emitting photons. And one amazing thing happened here. The photons are, you know, hitting another atoms, they're hitting another photons, and they also produce exactly the same wavelength and same photons as well. And in fact, this continues and continues because this mirror on this end is almost 95%. The reason why it's not 100% like this one, which is 100% reflective, the reason why it must have leakage. So in other words, the light, the photons will leak a little bit. Otherwise, if they don't do that, these photons will be trapped forever and we never get anything out. So I will explain more. What do we mean by that? Okay, let's put this down. This one shows better because Mr. Mayman used ruby and he was so genius. But why did he choose this? I will explain. Of course, you know, this is just a, you know, simple diagram, and you can see this is the tube, and then I will explain everything. You know, when we fed this ruby rod, what happened? Photons are hitting other photons as loud, like I said a few minutes ago. But the most important thing is this is causing chain reaction, and this was beyond my imagination. Wow, how could he come up with something so amazing that is causing chain reaction? Well, of course, you can't even compare with, you know, uranium, because, you know, when you have uranium-235, which is the, you know, light type of, you know, 238, if you have a, you know, neutron and then you bombard it with neutron, what happened? It will produce more neutrons and then it will chain reaction. Well, of course, this is not exactly the same way, but the concept is almost the same. So the photons is emitting more photons and then it's causing chain reaction. And the good thing is, this was genius idea. They have no place to go. They are trapped between these two mirrors, back and forth, and God knows they are going to be maybe astronomical, millions of photons with the same wavelength, so they come out from this side of the tube, which is over here. Okay, let me take this out, and then I have more. Well, of course, I have to explain something. This is going to be so amazing today because, unfortunately, I did not see why they did not explain what do they mean by 100% reflective mirror on one side and then 95% on the other side. And nobody explained what does exactly mirror do. Well, of course, they know they reflect. But this was year 2004, and my friend in University of Regis asked me, Vahan, can you come over for a day? We just made an appointment, and then can you come over and explain about the radiometer? I said, I will. Yeah, because that was, in fact, I just published this like 2 years ago, and that was great success. But now I added 2 more things. So I had to go to University of Regis and explain everything for them, and they love this. But why did I bring this radiometer in the equation? I will explain why. Let me put this up, you can see it. See, these are exactly like those, mirrors I explained. He was amazing scientist. I have to give you a little bit history of Mr. William Crookes. He was amazing scientist, probably one of the best experimentalists of the time. Always remember Michael Faraday, Henry Cavendish, and William Crookes. These were the best, probably by far the best experimentalists of the time. So this was accident. What happened to Mr. Crookes? He was measuring something, and then I always mentioned in my theories, anytime you do laws of physics, anytime you do any experiment, it must be thermodynamically enclosed. So in other words, if it's not in vacuum, it's going to be different, air pressure, and then, so many other things from the outside can influence you. So Mr. Crookes was doing some experiment, but unfortunately, it's not known what was his experiment, but I know that it was a sunshine that day, and then he realized he was amazing. 1800 we didn't have electronic scales or something like that. He was weighing with ordinary scales the way Mr. Some other people did, and then he realized his sample is not exactly the way it's supposed to weigh, and then this just led him to invent this. Well, of course, this radiometer is an amazing device. Let me show you. Most of the time in my theories, I correlate things. I try to connect everything, and this is amazing. Sometimes they call it toy, but it's a lot of physics, in a lot of science involved. So you can see this. It's exactly 1 centimeter, so you got the shiny, then you got the black. And the combination is amazing. Well, of course, it's not real powerful. It cannot be used in industry. It's just, for demonstrating of science. And I don't know why, I had to correlate this to solar sail, because this is amazing thing in science, but unfortunately, we cannot use it for propulsion in space. Well, of course, you can see it's the small one. This might be almost like 100 square meter, but the amazing thing is they are using laws of physics, for propulsion. So anytime you have shiny things, like let me show you. We can consider this like a solar sail. Well, of course, this is aluminum, but it's exactly like mirror. So you can see my face here. This, if the light comes here, photons hit on this, exactly right angle, everything is reflected. But unfortunately, they did not explain why. So anytime the photons come here, hit this surface in a right angle, this is amazing. Something happened amazing. If it's black like this, let me show you. 100% of the light will be absorbed. See, this is a black cloth. 100. And then if it's shiny like this, it will be reflect back. But you know what? You always know that, when you have like in the winter, you have like a, dark color, everything is absorbed. When you have a light color, white or, light blue, you are not getting that hot. So that's the reason why. So this is amazing. When we have the solar sail, what happened? The photon is hitting the surface, is bounced back. But what happened? The 100% momentum comes in when it rebounds 200% momentum. So what happened? That 200% momentum, well, of course, we know that the photons, they have no mass. But what happened is that there's laws of Mr. Sir Isaac Newton come in equation. Action, reaction. So 200%, so it's causing force on this, and then that force propel. But unfortunately, the bad thing about this solar sail is it's just an experimental thing. We cannot use for propulsion. The reason why sun's electromagnetic waves after the Mars is not strong enough to propel this. So most of the time, like our International Space Station, things like that, we use the solar cells, and then we use like electricity, so we don't have to do anything. So this is what happens. So if it comes in and when it's dark, 100% will be absorbed, but if it's shining like this, 200% goes out. So this is called solar sail, and always I do the comparison. And at this time, I have to mention somebody, someone so genius. His name was Max Planck, and then you must have heard about him. He was genius scientist, and then he was German, and then he explained black body radiation. What it means that you have something like this is called black, and then the photons hit, it doesn't matter, anything can hit. Photon hits here, everything is absorbed. But he described if something is 100% black body, everything is absorbed. If it's not, it will reflect back. And then the same thing happened here. You can see this is amazing device. And then this, this is like if you hold it in sunshine or, light, you can see now it's going, counterclockwise. Now I'm shaking, but practically it goes counterclockwise. The reason why you can see the black vans is going away from the thing. So there were so many theories for this. And by the way, this is a partial vacuum. James Clerk Maxwell, one of the greatest scientists, he described this that it must be total vacuum, but he was absolutely wrong. Albert Einstein said total vacuum, they were wrong. But finally, so many people after William Crook, they just explained exactly how this works. And then I had some good experiment that it's never been done in history, so I can show you. And before I do that, I have to explain what Mr. Planck did, Max Planck did. He was a very good scientist, and let me put this up. And he called this, this is a good experiment, I don't know who did this, but this is called cavity radiation. It's the same thing, or black body radiation. And then I had to do my own experiment. This is amazing device. You can see this is a box, and then if I open the box, you can see it is white inside. See? But the trick is over here. When I close this, you can see inside is completely dark. Yeah, I hope you can see. And I had to go so many steps further. When I put my radiometer let me show you. Well, of course, I can't do the sunshine now because I'm indoor now. Even if I put this, when I close the lid, and then I check with a small, light, my radiometer is not functioning, it's not working. Even if I take this, the sunshine is not going to work. But there's a science behind it. When the light or the photons comes inside, they go back and forth. All the walls, they reflect back and forth, and I have no idea scientifically how many seconds it takes, but they're absorbed. So you can see inside is completely black. Well, when I open this and I take it in sunshine, my radiometer will work. So this is called the cavity radiation or black body radiation. And this is an amazing experiment. You can see how precisely it shows. I had to do so many things on this, and then I will explain about the laser. If I get my hands from this is going to go counterclockwise. Of course, I can't let that go. The reason why my body has a infrared, it's not expensive. It's not a lot. But when I do that, what will happen, it will go. And then I had to analyze this so many times. This is the combination of Max Planck, black body, radiation, and solar cell, the way I explained. So practically those shiny vans and the black vans help each other. The reason why it is partial vacuum, if it's not partial vacuum, it's not going to work, because those vans are getting so hot, the black vans, and then that pressure is just pushing everything, and those vans are going round and round and round, and it's always counterclockwise. It means that the black vans are going counterclockwise, is going away from the thing. And then this is the second experiment. I did it. I hope you're going to love this. Let me turn this on. So in order to prove that this radiometer can work with not only electromagnetic wave from the sunshine, but also by infrared. So I turn my blower on. You can see. See, it's going counterclockwise now. So it's going the reason why the heat is working. See? So there's so many things, that could have been explained for the, shiny surfaces. But this is the way it works. And then if I put hot water in it, it's going to rotate. If I put cold water in it, it's going to go counterclockwise. So I put this in my refrigerator for 8 minutes, and then when I took it out, it was going counterclockwise. But overall, this can detect the sun's electromagnetic radiation. And amazing thing happened, and I remember this was a good experiment. When I put this in a sunshine, I have a special device, let me show you. Since the laser beam on this, I have to show you. See, this is a tachometer, and the laser beam can detect exactly what I did. I'm using this for laws of physics, but I had to use the same thing because this has 4 vans like this. So if I get 500 RPM on my my tachometer, I have to divide it by 4. So every time one shiny surface passes, there's a counter inside, electronic counter, and then it shows. So if I even put it in a shade, I measured with a great precision. It was like 100 RPM. When I put it on a sunny day, sunshine, it was almost like 500. The reason why it was more than that, but like I said, sometimes we got overcast. So if I put it in a shade, it's almost the same thing. But the shade I'm not talking about, inside the room, where the sunshine is, maybe a little bit 20 centimeters away in the shade. But there's a concept behind it, because electromagnetic waves can be diffracted. Let me show you here. Oh, yeah, I'm sorry, I forgot something important. And Max Planck came up with this idea, which is so important. What do we mean by the energy of photons? Energy of photons means H multiplied by F. So F is the frequency, and this H is a constant, it's very small, we don't worry about that. And then the point is, always when you have, lower frequency, you have more energy. You can see in electromagnetic waves, it's the same way. Let me just I have some over here, you can see. So you can see here, we have, like radio waves. You can see how big the wavelengths are, and the frequency is less. And the gradually is just increase. And by the way, this is the infrared, from, see, this then goes to the visible light and go all the way to X-ray and all the way. You see, the smaller the frequency, the wavelengths, the more power they have. So this is the way that electromagnetic works. So this was his formula, which is so important. And always, when we have more frequency, we have more power. And this is the one which I explained that, light is so amazing. Imagine, this is not ordinary light. This is coherent, or, we call it laser. Even the laser is getting diffracted. If you have a small opening like this here, see the light goes around it. Imagine if you are in a room and there's a big wall or, big, partition in front of you. Even if I go behind that partition or wall, I can see the light is still there. The reason why light is getting diffracted. The sound is the same way, but overall the electromagnetic wave. The reason why I show this, because I just wanted to show you that even the coherent light, which is laser, also getting diffracted. You can also polarize it, because this is the way Michael Faraday did, and then he proved that you can have interaction of magnetic force with the light. Then he proved that he could do it. Then they call it Faraday's rotation, and you can see you can polarize it. What do we mean by that? We can eliminate the magnetic field, because the light is electromagnetic, and then you can polarize it and just get the electric field. I have to mention something important. Light, or the sunshine, when we have like a sunshine, normally the electric field of sunshine, or is almost like a quadrillion in a second. We're talking about 15 zeros. The electric field is fluctuating up and down, up and down, up and down, or left and right, whatever the thing is. So it just 15 zeros, quadrillion time. That's the reason why I used to live in Westminster for 18 years. Colorado is so cold. One day I remember it was minus 10 degrees. When I came outside, and then I saw the prairie dogs, they were playing, and I saw that, where the sunshine, when the sun shines, that snow is melted more. When the sunshine is the backside, that side was exactly the same, like 2 inches, 3 inches of snow, it was untouched. And then I said, well, the temperature is not good, it's minus 10. So that what happened, sunshine's electric field is melting everything. And you know what? This is not coincidence. Always I remember when I analyze, laws of physics, there are 3 laws is so important. Henrik Lorentz laws, Michael Faraday's induction law, and then solar sail and electromagnetic waves. And by the way, the next project for me is going to be electromagnetic wave, and then I will explain Michael Faraday, James Clerk Maxwell, which is one of the greatest scientists. And you can see, if the Henrik Lorentz is not perpendicular like this, it's not going to be effective. So electromagnetic wave does the same thing. Everything is not coincidence. It must be 100%. That's the reason why when I said light photons hit here in a right angle, it'll be okay. But what if it hits in an angle like this? It's not going to be powerful. It will have propulsion, but less. And of course, we know that laser is used in every aspect in our life. Let me put this off. as you know, let me see if it's okay. Yeah. As you know, the moon is 238,900 miles away from us, or 384,400 kilometers from us. In It was in 1969. I mean, you may not believe they measured from the Earth to the moon with great precision. And there is no exaggeration. It was in a few centimeters. That's how precision. But you know what? They were so smart, they had to put reflectors like this, the moon. But I have no idea how many, because they don't explain anyway. But I have no idea how big these reflectors are. And as you know, the moon is tidally locked, and then it goes 27 days to go round one time. And then they had to know exactly when to shine this laser beam, you know, when it was going to the moon and coming back. They just calculate the time, and this reflector shows exactly the same distance, 384,000 kilometers from the. I mean, is it possible that we could have done this otherwise without the laser? I'm sorry, I don't think so. Because the reason why laser is so coherent, can go, it doesn't get spread, it goes in a long distances. And that's the reason why they could do this, and then they measure the precision like this, you know, and then not only moon. Well, of course, I have no idea we can go maybe beyond moon. It's a little bit difficult because we've never been to Mars or the other places. Probably we can't do that. But I mean, when we talk about 384,000 kilometers, is beyond my imagination. The precision is so good. So the light was reflecting from here and coming back, and the other one was, it's almost like a radar. But in radar, it's so different because we're using the radio waves, which is some of them are 2-3 meters or 10 meters. But this is different. Laser is so different. But anyway, that's the way they did. And I'm glad that laser changed our life. And the most important part in my theories is the application of the laser. Because I remember when I was so young, people would talk about, eye surgeries and things like that. It was out of question those days, to do, surgeries with a laser. Let me put this up. You can see. Well, of course, I have so many, but I had to only print 2 of them. I remember those days they used to say, yes, I had a surgery with my eyes and so and so. But I had no idea how sensitive your eyes are. Is it possible to, cut your eyes with anything? No. But the laser is so sharp, can do that. Well, in a few minutes I will explain. You can see here, see how sharp that beam is, and you can see, oh, I'm sorry, I have this upside down, I'm sorry. You can see how sharp it is, and it's getting to your retina, and then can change. Even they can do, if it's a blood here, they can clean it. But it's amazing how they could that. And this is another one. I remember we used to work with a company in Denver, and that was a huge corporation called Denko, and they were billionaires. I mean, that was the most important company I've ever seen with laser. And then I had to go and then get some discs. Like aluminum, sometimes copper, sometimes so many things. And see, this is like a steel. They can cut to almost like 1 inch or 2.5 centimeters steel, and you can see this is laser. So anyway, because we were customer, and then the operator told me, Vahan, you can come over and touch this. When he was cutting this, it was almost like 1 centimeter, steel. He was cutting, he said, touch this. When I touched that, it wasn't hot. But imagine if you do this with any blowtorch, that is going to be so hot, that's going to be like, red. So there is no way you can touch it. And then when I touched it, I realized it was, it was good. But the precision was unbelievable. he was programming in his computer and then cutting everything. And these are the applications. Well, of course, there's so many. I'm hoping that, I did not, miss anything. Let me put this up. You can see. Like I said, so they can cut through any steel or any other materials. Surgeons use laser of much lower power in eye surgeries and cosmetic procedure. A laser beam cuts tissues more precisely than a scalpel. That's a device. The heat from the beam burns severe blood vessels instantly, preventing bleeding. Laser also used to clear out deposit, clogging arteries. Imagine, that is amazing inside your body. I remember last time we talking about the optical fibers, how they can use humans' life, how they can save humans' life. Laser is doing the same thing. If your arteries, something is clogged, they can open it up. And then making precise measurement, the way I explained for the moon, and then distances to moon and so and so, and then a low-cost diet. Lasers are used for retrieving data from the compact disc. Imagine, so every time you listen to the music, every time you watch DVD, and the laser is going through that disc, and there's so many fine lines over there, like the old days, is reading all the information, and that you can see, or you can listen to the music, or you can watch videos and so many things. And the one important thing is about the barcode. I remember in Los Angeles, it was like 46 years ago, we used to live in Los Angeles, and then we used to go to supermarket. It would take forever. It was almost started, the barcode, but they had to put everything in the cash register, and then, but nowadays it's so, I have seen some people are doing like 100 items in less than a minute. That's how fast it is. So imagine, without the laser, it could have been impossible to do that. It's just out of question. Photocopies. It's been in use, God knows, for maybe 50 years, and our life depends on photocopies, and then the printers, and how good they are. And then in scientific research, I have to give you one example. When I was in Westminster, and then I remember it was 2003, so we became friends with so many physicists over there, and one of them was Dr. Eric Cornell, and his colleague was also good physicist. His name was Carl Weinman. So they did something extraordinary. I don't know how they did it, but that was beyond my imagination, beyond my comprehension. How could they go that low? Because nowadays we use like liquid nitrogen, for superconductivity and so on. So liquid nitrogen is nothing compared to, when we're talking about 273, absolute zero. So what they did was amazing. But the secret for Mr. Carl Weinman and Eric Cornell was that they got a Nobel Prize for this in 2003. They could go to 20 nanokelvin. And imagine 20 nanokelvin is amazing. No human being or no scientist has gone that far in science, and Mr. Eric Cornell did it, and that was a history. And they worked on a Bose-Einstein condensate, and they had to use, rubidium, and I don't know how they could do it. It was a gas, but how could they choose 2,000 atoms, which is beyond my comprehension? They used 2,000 atoms, and then they went all the way to 20 nanokelvin. But the laser was did 90% of the job, and the 20% was done by evaporative cooling. Anyway, they did it, and then I'm sure that this will be remembered forever. And since then, 2003, nobody has gone that far. I mean, almost close to absolute zero, because laws of thermodynamics tells us it's impossible to get to the absolute zero. And I think they did a history, so they did a good job. And then this was scientific, and also fiber optics, I explained last time, and then communication, guiding missiles, and also holography, which don't have the picture unfortunately, and construction, because my friend is an architect. He said that is the most precise measurement we can do with this, and then also in architectures. So they used almost for everything, and like I said, it is used in every aspect in our life. And I'm hoping next time my theory is going to be electromagnetic waves, and I will explain that James Clerk Maxwell, how he changed our world with electromagnetic waves, because it's so important in our life. Well, we have the electromagnetic waves, and now we have the sunshine, and then we have the photons, and so many things. And Mr. Max Planck, he just explained everything, and it was so unknown before Max Planck. What do we mean, by the black body radiation? Why things get so hot? It says everything is inside the material. Like I have something black like this. It's the atoms. It's inside the black things. So. And then I had to use this, I missed this one. I had to use this laser, this is infrared. And then when I shine this on my solar cell, everything was reflected back 100%. But imagine, when I put this under the sunshine, my solar cell was showing 100 degrees. This was showing 161 degrees. The reason why Mr. Max Planck was right. So absorption, that's why that radiometer works. And you can see how important in our life is. I'm going to show you one. See, you can see here, that part is the reflective part. And they never explain why they have, well, of course, we know that everything is reflected back, photons are reflected back. And this is another one. See, you can see everything is shiny here, so it doesn't matter. See, it's all around. See, you can see it's reflecting back. So in other words, it's enhancing the photons. So, and I'm hoping you guys would love it. And then I had to make my own radiometer. Let me show you here. See, it's like this. You can see one van is shiny, and the one van, the opposite side is black. And well, it's a great invention, because the reason why we can check the intensity of the solar, radiation. And I'm hoping you guys love this. And then every time you have any question, you can email me. And then I think I show you my email. It's exactly my name. But let me put this up one more time. I think I forgot to tell you my email. Yeah, I missed this part. I'm sorry. I have to put this up one more time so you can see my email. So anytime you have any question, I'll be happy to answer your questions. Let me put this up. Lasers by Vahan Davoudian, physics experimentalist, and this is my email, Vahan Davoudian, exactly my name, at AOL.com. So anytime you have any questions, be happy to answer, and I'm hoping that I cover everything. And if I missed anything, you can go ahead and email me. I appreciate that. And from now on, I decided to do every 2 weeks. And then I'm hoping that you guys would love it, because 1 month is such a long time. So in next 2 weeks, I'm gonna have electromagnetic waves, and then I will explain about James Clerk Maxwell, and then another 2 weeks I will have the color perception and so many other things. And I'm hoping I cover so many things, and I'm hoping that every time I come up with the new ideas, so in other words, whatever the other professors and universities or the YouTube some people did, I have to add more. And today I add the solar sail, and then add some other things about the reflection, and I'm hoping for the electromagnetic wave I will add more. And thank you for watching, and then if you like this video you can subscribe, and like I said, anytime you send me an email is an encouragement, because see, in laws of physics, if there is no feedback, the oscillation always causes feedback. Always the feedback is important. If there is no feedback, I have no idea how I did it. And thanks a lot for watching, and appreciate it.